Okay, we're going to start off with our first video for Chapter 11. Coming off of thermodynamics, we were thinking a lot about spontaneity. Is a reaction going to go forward spontaneously? But we didn't really answer any questions about how long would it take. There are spontaneous reactions that can take hundreds of years. And so kinetics answers the question of how long. Just because a reaction will go forward, if it doesn't go forward fast enough for it to make a difference in your life, maybe it's not one that you're interested in. All right, so kinetics is a very practical area of study. All right, so when we talk about how long will it take, right, we are talking about rate. Now, you are familiar with rates, whether you think of it that way or not. You think about average speed, right, as distance over time, and similar to rates of chemical reactions. Now, we are going to skip that first section on ozone depletion, and we're going to go straight to section 11.2. There are going to be two main things that we determine, that we learn how to calculate in this chapter. We're going to talk about the rate of a reaction and how it's defined. And then we're also going to talk about how the rate is measured. So when we think about rate of a reaction, right, let's make sure we define that. This is going to be based on concentration. All right, so the rate of a reaction is defined as change in concentration over a certain amount of time. All right, now that could be concentration of starting materials or products, though typically we'll be looking at starting materials. Delta is your symbol for change. When you see brackets, that is going to indicate that we are talking about concentration, most commonly molarity in chemistry, over a change in time. So how did the concentration of your starting material or your product change as time moves forward after the reaction started? Now, the rate is going to be in pretty specific units, right? That you've got concentration, so that's moles per liter, over time, which is typically going to be in seconds. All right, so the unit for rate is moles per liter per second, or moles inverse liter inverse seconds. This is affected by stoichiometry as the reaction proceeds, right? For one, you know the starting material, the amount of starting material is going to go down, the product's going to go up, but the rate of the decrease in starting material and increase in products isn't always the same. It's affected by their stoichiometric coefficients. So there is something that you have to add in here along with sign. All right, you're going to have the rate of if you're looking at the product, that's going to be an increase in concentration over time. And the rate should be a positive number. If you're looking at the starting materials going away, there will be a negative to counteract that negative change in concentration of starting materials over time. To account for stoichiometric differences, you will also put that stoichiometric coefficient on the bottom, right? So stoichiometric coefficient of starting materials or of products. And that will make sure that even if there is a difference in that mole ratio, the rate will still be the same. Now, how does that play out? So instead of working the problem in the slides, I have over here a problem that's in your book. So we're looking at the production of NO2 from nitrogen and oxygen, right? This was studied, and the rate was determined to be 2.5 times 10 to the negative fifth moles per liter per second. Now, that is the rate at which the nitrogen was consumed, right? So that is the rate that the N2 is going away. If we want to know what is the rate of the production of NO2, well, hopefully, because it's an easy equation, you can see that you just have to multiply it by 2, right? Because the delta of the concentration of NO2 should be divided by 2 times change in temperature. So if we're just trying to find the rate at which, and I'm going to rewrite this here, if we're just trying to find the rate at which the NO2 is forming, right, then we're just going to do 2 times 2.5 times 10 to the negative fifth. And so the rate of, if we're just concentrating on the product here, is going to be 5.0 times 10 to the negative fifth moles per liter per second. All right, now when we are discussing rates, it's important for us to understand what rate are we talking about. There is an average rate and there is an instantaneous rate. Now, we can think about these definitions in just a moment, but again, let's go back to our driving analogy. Your average speed. You may have an average speed from the time you get into your car in the parking lot to the time you show up at Rallis, right? But you know, and that is just simply the distance that was traveled divided by time. And let's say on average, you went 55 miles an hour. You know, at any given instant when you're in the car, you could be going slower while you're on the street where your house is. You may speed up as you turn onto University. You may go even faster as you get onto Highway 47, assuming that we're all taking the same routes to work or to school. So the same is true for reactions. Reactions don't always proceed at one continuous rate from start to finish. And so an average rate would take a look at the two concentrations at different times and calculate the slope. And there is actually a picture of that here. So it would be this line here. You would look at, it looks like T0 versus whatever this time is. And the slope of that blue line would be your average rate. Instantaneous rate would be the rate at that single moment. Comparatively, what is the actual speed at which your car is moving at a given moment. And that is going to be the slope of this green line. That's going to be a line that is tangential to the curve of your rate over time, right? Which is usually a curve and not a straight line. So think about this example here. If you've got a candle burning in a jar and you put a cap on it, that candle is eventually going to go out, but it is not going to shine this bright and then all of a sudden go out. Over time, that as the oxygen is depleted, as the concentration of the oxygen goes down, the combustion reaction is also going to have a slower rate, and the flame is going to get smaller till eventually it runs out and it dies. So the instantaneous rate in this picture would be of the oxygen being burned up would be different than the instantaneous rate in this picture. Most of the time, I would say when we are dealing with kinetics, we find ourselves interested in instantaneous rate. Now, as we move along into rate laws, how are rate laws determined? Well, there are two types of rate laws. They're mathematical descriptions of reaction rate and its dependence on concentration, and there are differential rate laws and integrated rate laws. We're going to start with the differential rate laws. The differential rate laws have this general form. So if you have some, let's not use a highlighter. Here we go. If you have some reaction, X and Y reacting to form products, your rate law is going to be your rate equals K. K is your rate constant times the concentration of X raised to some exponent times the concentration of Y raised to some exponent. These exponents are orders or reaction orders, right? So M and N are reaction orders. M and N must be determined experimentally. They have nothing to do with the balanced equation, though sometimes that will match up. You have to determine them experimentally, and we are going to cover that. Before we figure out how to determine M and N, let's talk a little bit more about them, about what orders of reaction are and what they mean. So each reaction order, M or N, is talking specifically about how the concentration of that substance affects the rate. And so M is determined experimentally for X, N for Y. They are going to be usually whole numbers or fractions, and it's typically going to be from 0 to 2. And the overall reaction order would be M plus N. So you add up the individual reaction orders for each component, and you get an overall reaction order for the whole reaction. So for instance, if we have these two rate laws here for generic reactions between A and B, the reaction order, right, for A is 2, for B is 1, and then overall would be 3. Now, individual reaction orders usually aren't more than 2. Overall reaction orders can be greater than 2, of course, can be bigger. If we look at this last example on this page, A would be 1, B would be 1/2. That's a possible reaction order. So overall, it would be 1.5 or 3/2. Right? So pretty simple if you already have a rate law to determine the reaction orders and the overall reaction order. But what if you don't already know the rate law? So that's where this page will help us. Before we move into actually determining it, let's talk for a minute just about K. K is your rate constant, and it gives you important information about the rate, right? Is this going to be slow versus fast, right? If it's really small, then it's going to be a slow reaction. A really large K is going to be fast. The units of K depend on the reaction order. All right, so for example, a first order reaction would have units of K that would be inverse seconds. A second order reaction, I have it written down. Oh, here we go. Would be liters over moles seconds. Now, the reaction order, the units of K are pretty much just whatever they need to be to make the equation make sense. You don't have to memorize them, but it is important to pay attention to your units. Okay, so if we are going to try to determine our rate law, there are two ways. So the one way is to look at graphs, and we will look at that when we get into integrated rate laws in the next video. But another way would be to look at data, right, from performing a reaction. to look at instantaneous rates, typically initial rates, like you see right here, as you change the concentration. Now, as you change concentration of a starting material, how does it affect the rate, and how do you know what reaction order what reaction order do you have? So we're going to start very simply. We're going to look at a reaction with just one reactant. When we get to our example, it'll be something like a decomposition reaction here. So to look at our examples, though, first we're just going to look at measuring graphs. Here we go. We're going to look at this very, very simple rate law where you only have one reactant. We're going to look at the effect on the rate if the concentration is doubled. But we could triple the concentration, we could half it. We're looking at the relationship between what we do to the concentration of A and what happens to the rate. So if we double A, right, that's the parameters we're looking at here, and the rate is unchanged, so the rate is not affected by how much A is present, then N equals 0. This is a 0 order component. Now, that doesn't mean that you could have no A. It's just saying that as long as some A is present, the reaction is proceeding at the same rate, and that would be a 0 order. If we double the amount of A and the rate also doubles, this is a first order reagent. If we tripled it, then the rate would triple. If we halved it, then the rate would half, right? And N equals 1, a reaction order of 1, means that whatever you do to the concentration, the same thing happens with the rate. Okay, so when we look at a second order reagent, then what we're going to see is that whatever we do to the concentration, it's going to have an exponential effect on the rate. So if we double the concentration of A, then the rate is going to quadruple. All right, now how do we determine these reaction orders with data? So we're looking at, for instance, in this example, we're looking at the decomposition of dinitrogen pentoxide, and we're starting with 2 experiments. You have to have at least 2, so that we can show when we change the concentration, how is that initial rate affected? And from this experimental data, we see that we tripled the concentration as we went from experiment 1 to experiment 2. And how did that affect the rate? Well, the rate went from 9.0 times 10 to the negative 7th moles per liter per second to 2.7 times 10 to the negative 6th, or 27 times 10 to the negative 7th. So it also tripled, right? This means that what happened to the concentration was reflected in the rate. That is going to be a first order reagent. So now we can write out our rate law, or almost. Rate is going to equal that rate constant times the concentration of dinitrogen pentoxide raised to the power of 1. So if you also don't have to write a 1, but that would be the reaction order, the for N2O5. Now, to solve for K so we can complete this rate law, we just need to choose experiment 1 or experiment 2 and plug in and solve. All right, so K is going to equal the rate divided by the concentration, which is going to be, let's say that I'm going to do experiment 1, 9.0 times 10 to the negative 7th, and that's moles per liter per second, divided by 3.0 times 10 to the negative 3rd moles per liter. All right, and so K equals 3.0 times 10 to the negative 4 inverse seconds. So I know my rate law and I know K. Now you should get the same K value no matter which experiment you use. Let's expand a little bit here and let's look at a reaction that has more than one starting material. Here we go. If we look at the reaction of nitrogen dioxide and ozone, we can study this rate law. So we want to figure out, right, what is the reaction order for NO2 and for O3. But we're going to do that based on, now we need at least 3 reactions or 3 experiments, because we can only compare we can only alter one variable at a time to truly understand the reaction order. So if I want to figure out the reaction order of NO2, then I need to keep O3 constant. So I'm going to look at 1 and 2 to figure out the reaction order for nitrogen dioxide. I see that as I go from 1 to 2, I am doubling my concentration. And so what happens to the rate as I go from 1 to 2? It about doubles, right? So that's going to be a first order reagent. Now, if I want to look at, say, the ozone, then I need to find 2 experiments where the NO2 is not changing. So I couldn't compare 1 and 3, even though O3 is changing. I have to compare 2 and 3. Now, from 2 to 3, the concentration of O3 is doubling. As I go from 2 to 3, for rate, I also see that it's doubling. Why did I put a 3? It is doubling. So this one is also first order. Again, if I am asked to solve for K, and I am, then I just need to pick an experiment and I need to plug and chug and solve for K. It looks like I chose in my notes here experiment 2. Why not? Right? We're going to have our rate is 2.1 times 10 to the negative 5th moles per liter per second. And that equals K times 4.6 times 10 to the negative 5th moles per liter times 3.0 times 10 to the negative 5th moles per liter. What that gives us is, and I'm just going to write it up here, is a K that if I rearrange and I solve, I find that K equals 1.5 times 10 to the 4th. And because this was overall a second order reaction, right, 1 plus 1 is 2, the units are not going to be inverse seconds like they were here. The units are going to wind up being liters per mole per second. Right, so I figured out the rate law and the rate constant from data. In the next video, we will tackle integrated rate laws.